Good afternoon, everyone. Thank you again for that warm welcome. And I'm extremely excited to be here this week at AWE and really share in that vision of human-centric AI. And we at TDK believe that smart glasses is the most natural interface between AI, people, and the world around us. At the core of smart glasses, at TDK, we're enabling sensors. Sensors that connect us to the glasses, sensors that take the data from the real world around us into the glasses, and those same sensors who produce the data that will fuel the next generation of models and spatial compute. My name is Omar Abed, and I'm the CTO for TDK InvenSense, and I'm excited to walk you through the sensor technologies that TDK is bringing to enable the next wave of smart glass products. Over the next 25 minutes, I'd like to walk you through this exponential growth that we've been seeing in AI, how smart glasses is the most natural interface to harness that power of AI and also connect us to the world around us, how sensors and particularly power consumption are going to be key factors in enabling the rapid growth, and what the future might look like as we come to address these challenges. So let me start with AI. And really since that moment in 2022 with the ChatGPT takeoff, and what we've seen is just an exponential tear of the technology through the industry impacting the world around us. And really when I think about this, I think about three compounding factors. The first is in the hardware side. What we're seeing is a continuation of Moore's Law with full stack software, and that's helping us double compute power roughly every 8 months. Layer on top of that, the model advancements, the efficiency gains, seeing that also double roughly every 8 months. And more recently, the takeoff of agentic AI, the autonomy that that brings with respect to harnessing this power, doubling every 7 months between intervention. When we layer these three exponentials on top, again, the human brain thinks very linearly. It's very hard to anticipate where we'll be in even 1 to 2 years from now. But it's an exciting moment. And again, sensors are at the core of that. Sensors are creating the data that are feeding the models and efficiency, but also the data we can create synthetically by understanding how sensors interact with the world is also going to be key. And we at TDK are at the forefront of both of those. And as we think about this power that's coming, that AI is enabling, again, and that human-centric perspective, how do we harness this exponentially expanding power and intelligence? Well, I don't have to explain to many of you. You've seen it on the show floor or in some of the talks this week. But imagine a personal assistant with you. You leave the house and you wondered if you left the stove on. Or maybe you get that nudge. You need to leave now to catch that meeting in 5 minutes. A personal assistant that's with you will always make sure you're in the right place at the right time. Or it's a high-pressure situation. You're on the operating table, and things aren't going as planned. Having that extra pair of eyes with you can help you make the right decision so that the patient gets out safe and with a fast recovery. Or perhaps you're in a new city and trying to get around. Or maybe it's the same city you live in, and there's traffic. Again, smart glasses can be that application that connects you to that real-world situation while getting you there safe and sound. Also, we have colleagues all over the world. The world is getting smaller. We can connect it real-time translation so that each person can speak in their mother tongue to enable a deeper connection. We also know factories are getting more automated. And so technicians and operators are having to cover more of the factory floor. And with smart glasses, you can hear and see the factory floor and become more efficient as well. And these are just a few of the different use cases that are emerging, and then again, as you've seen today and this week on the show floor. So it's a really exciting moment as these glasses proliferate to see what will happen. But the fundamental question at this moment in time is, why aren't we all wearing them already? Well, between the vision I just painted and where we are with the products on the shelves today, there still remains a gap. First, the glasses of today are just too bulky to be worn all day. Privacy has also been in the news in an unfortunate way. And I think that's going to need to be addressed if we're going to be able to pass, as was mentioned earlier in the week at the keynote, the cafe test. You walk into the cafe and people aren't running away from you. Short battery life is also a challenge. People want to be able to wear their glasses all day. Style and social stigma. One is how we're perceived. Again, glasses are on your face. The first thing people see when they see you is your face. This needs to be have a good style, but also in the way we interact. The user interface needs to be seamless. Because the number of glasses in the field is relatively small at this moment, there's also limited applications. But again, we're seeing that emerge over time. Combining all these limitations, and on top of that you have a $1,000, maybe $2,000 price tag, it's really been relegated to the cutting edge and people early tech adopters. So when we see this challenge, the question remains, what role do sensors have in closing these gaps? Well, when we think about a sensor, fundamentally we're always trading off three things: performance, power, and size. The good news here is that with the technology and where we are today, the performance level of the current sensors are good enough. We can actually enable a lot of the features and functions that smart glasses are hoping to enable. The challenge resides with power and size. And to solve that, first with power, we really are targeting all-day wear, as I mentioned earlier, 8 hours. For that to happen, we're going to have to draw the average power consumption under 200 milliwatts. With respect to size and weight, what I'd like to see us go for is the disappear effect. You put the glasses on, and 2 to 3 minutes later, you've forgotten you're even wearing them. For this to happen, we're going to need to drive it under 50 grams. And these are significant gaps to where we sit today. With respect to sensors and weight, sensors comprise and actuators comprise about 15% of the total weight. Our goal in the next generation of sensor products is to drop this by 30 or more %. With respect to power, sensors are only about 7%. We will continue to reduce power by 30 to 50% here, but the bigger impact is going to be on the system level with pre-inference and edge AI. I'll touch more on this later, but this is going to be the revolutionary change that we're going to see over the coming years. Before we get to power, though, I want to break down the size challenge. So we see the latest and greatest smart glasses are coming in that 70 to 90 grams kind of in weight. When we look at the breakdown, again, you're going to always have about 25 to 30 grams for the frame, but sensors are directly or indirectly contributing to about 40% of this weight, and a much significant more percentage above the frame itself. What we're doing is we're trying to, because again, we have 10 to 20 sensors per pair of glasses, limit the number of wires connected to communicate and interface with the sensors. Today that can be upwards of 4 or 5 connections down to 1 to reduce wiring, which is about 4%. With cameras, particularly for gaze detection or inward looking, we're looking to replace that with time of flight, ultrasonic time of flight sensors, significantly reducing the 10% of weight that those cameras consume. We also are talking about power. As we continue to draw down power, we can continue to reduce the battery size. Batteries are about 13% of the total weight. And the sensors and actuators themselves are about 15%. And as I touched on, we want to reduce that by more than a third in the next generation. So overall, we can be a significant force in enabling that next generation to enable that disappear effect of less than 50 grams. But I want to come back to really the big challenge at heart, which is power. Power really limits our battery life for that all-day wear. But as we bring down the battery size as well, we can improve size and weight. And I'll also touch on it later, but this challenge also enables privacy. And by keeping data on device and computing at the edge, we're going to find that these things can actually go together. This evolution can merge in a nice way to address some of those core issues I touched on earlier. As we continue to evolve, we expect increased adoption and acceptance. More users will buy. The hardware ecosystem will expand as more investment is drawn in. More users will come again. And then the apps will develop and the operating systems will get more mature as well. And the flywheel begins to take off. And I think this will be a key test for whether smart glasses can fundamentally take off. So with respect to the flywheel and why this is so important, I want to take an example of 2 applications, TWS, wireless headsets, and virtual reality. In one case, the flywheel took off with TWS, whereas in industry we sell more than 500 million units per year. In the case of virtual reality, about 10 million. So what was the difference? How did the flywheel turn on in one case and not in the other? In the case of TWS, there's an ambient presence. You can consume the digital content while still being connected to the world around you. In the case of VR, it took us away. Battery life is also a key factor, 4 to 6 hours. And at TDK, we're working on even lower power sensors to take this up to a full day of 8 hours. In the case of virtual reality, we're talking about under an hour. Weight was also a factor I touched on. TWS comes in under 10 grams, with many headsets being even less than 5. In the case of virtual reality, we're talking about 0.5 kilogram on your head. And as a consequence of these factors, I believe that TWS has become now a necessity or utility that most people carry around with them every day, whereas virtual reality is really a novelty relegated to gaming and specific applications and use cases. So keeping this in mind, I want to go forward and touch on how sensors are integrated within the smart glasses. I'd like to show you a presentation so you get a real feel for how that all comes together. Very good. So hopefully that gave you a sense of how all these sensors come together in a pair of smart glasses. And so when we think about today's modern pair of smart glasses, we see about 10 sensors per frame, and that's growing closer to 20 over time as we see these new products being launched. So what goes in? We have IMUs, which are your gyroscope and accelerometer for motion detection, TMR magnetic sensors for rotation and user input, microphones, of course, for audio input, and ultrasonic time of flight for gesture detection, gaze detection, and for detecting wearability. So in the case of TDK, we're really focused on power as we believe this is the fundamental challenge. And in each class of product we're the lowest power in the market. But it's not just about the sensor that goes in. It's also about the functions and features they enable and driving the power of those features and functionality down. So for example, of bone conduction. So bone conduction uses an accelerometer with the microphone to determine that the voice that's being spoken comes from the wearer and not from some random voice outside, so you always stay in control of your glasses. Hinge angle allows us to turn the power in the system on and wake it up and save power when the glasses are closed. Optical image stabilization is also key. Obviously we have cameras, and as you're moving, you need to stabilize the image or the video to make sure you get the right quality and conclusion as you compute. Head orientation is also very important using the motion sensors, and particularly as we implement features like SLAM, we're going to overlay augmented reality on the world around us. Activity tracking also comes for free with the motion sensing, haptic touch with feedback, as well as position sensing, which is core in that example I gave earlier for navigation and having true north and true heading. So again, really we're focused on not just low power sensors, but how those sensors do computation at the edge on device to enable the lowest power features. When I think about this hierarchically, we break it down from what I call the edge squared, and that's the sensor itself. Remember, the sensor connects the device to the world around us, taking in real world data and bringing it into the digital domain. Here, the power is lowest and the latency is lowest. And again, we can increase the distributed compute. So again, we're talking about acting as a gatekeeper with pre-inference, while also driving power under 1 milliwatt and under 10 milliseconds of latency. In the event we have a task that's a little bit heavier, we can partner with the SoC, hand off the task, and something like a Qualcomm chip can take that and then do the compute, of course with more power, but still keep the data on device with this edge compute solution. And I think over time, as I'll show, more and more of the compute will be done on device at the edge. In the event we need to take the the data up to the cloud, we also want to leverage compression. We don't necessarily need to transmit all of the raw audio content or video content or pictures. We can send metadata to limit the power consumption and reduce latency. But it also will come back to protect privacy as well. And when we think about this power challenge, actually we have a real-world example that all of us carry with us every day, which is our brains. If you take the latest technology in the server rooms today, to create human-level compute, you're going to consume about 100,000 watts, give or take. Compare that to 20 watts for a human being. Put in perspective, we're talking 400 to 500 calories or a hamburger. So from this lesson, we can take a lot of inspiration. A couple of points as we think about the challenge with respect to smart glasses. First is the pre-inference I touched on, where the sensor is deciding whether information is relevant or not. And as a human, our experience is that our attention is not everywhere at once, all at once. We can see everything, can hear everything, but our attention is usually placed on something that's relevant to us. We're going to want the glasses to do the same and not burden the SoC with all of this compute. Context-aware compression is also important. So again, really compressing down maybe a period of time or a picture into what is most relevant. Things like gaze detection allow us to do that, to really focus on the object where our attention is, rather than a whole scene. Analog processing is another key dimension. The real world operates in analog. So by processing analog on the sensor, we can save in the digital conversion, which leads to power and latency improvements. And again, this is an exciting new area in AI, analog AI, where today most of AI is done digitally. And last but not least is decentralization. When we go back to that server, that 100,000 watts, a lot of that power loss is in the movement of data from memory to compute and back. By co-locating memory and compute, particularly at the edge, we can help improve the power consumption dramatically. What I'm really excited about, again, is this evolution of edge AI. Over the last few years, a lot of investment has been made, but unfortunately not a lot of return. But I think the best years are in front of us. I expect over the next 2 to 3 years, as the technology continues to mature, as I touched on, Moore's Law continues to play out, the models continue to get more efficient, we're going to be doing a lot more compute on the edge. This also helps us distribute the heat dissipation as the compute gets spread across the SoC and the devices like sensors, but also allows us to protect privacy. This is an exciting moment for edge AI companies and companies driving innovation in this space. When we look back, historically, sensors a couple of years ago just spewed raw data. You were just getting raw audio, raw video, or motion data, and then it was up to the SoC or the cloud to make sense of it all. As we look to the next few years, more and more this pre-inference and edge inference is going to drive the way devices work, which is going to allow much more savings in terms of power and size. And as we think to the future, to 4 or 5 years from now, the neuromorphic adoption and design will take over. And I think more of the compute will be located at the edge on device. And you can see that with more than 2/3 of the compute staying inside the glasses. To give you a sense of how we at TDK are pushing that forward, let me give you a sense on the vision side with Isight, a product that we're launching that uses gaze detection to process audio, or to process video, rather.
This is a traditional Korean hauhae mask, specifically called Yangban-tal. This is Dongdaemun Design Plaza. It is a cultural complex for design and fashion exhibitions. Do you want to know more about the architect? Zaha Hadid was an Iraqi-British architect known for fluid and futuristic designs. This is an instant meal cup from Hatbon Cup Bon. If you buy 2 or more of the listed cup rice soups, the price is discounted from 4,800 won to 3,000 won per cup.
AIsight. So hopefully that gave you a sense of what this edge compute can do. Again, we're taking the sensor data and compute on device, on the edge, to be able to execute functions and features like this. So it's really exciting where this is all going. Now to close this out, I really want to make 3 last points, close with 3 slides, and coming back to some of those core challenges we discussed earlier. First is privacy. Again, fundamentally, if we cannot address as an industry this issue, adoption will always be limited. But I think by doing more edge compute, we keep the data, your data with you on device. And I think that's going to be key as more and more of that stays with the glasses. And the second is the context-aware compression. Again, taking where the attention is, compressing the data, and only sending metadata to the cloud, we can also preserve by not sending raw video or raw audio up and protect privacy through the devices on the edge. The second is the road to all-day battery life, power. Today's glasses consume 1 watt or more. And when we break that down, I think 3 things are fundamentally going to have to change for this to really take off. The first, as you can see, more than 60% of the power is consumed in the display. And I think there's a lot of companies looking to innovate in this space. And as we bring new technologies in display side, I expect several breakthroughs over the coming years that'll help drive that down. When we talk about component count, again, sensors in the SoC are still a big driver of power. We're going to have to work on, again, harnessing Moore's law and improvement in models to drive down that power consumption, but also the pre-inference and edge AI. So I think as we use the system, we're really going to want to limit and duty cycle those power-hungry components and leverage, again, edge AI to drive power down to achieve that 200 milliwatt target. And ultimately, as I touched on earlier, the flywheel. Our goal is to get the flywheel to take off. And when we look at this journey, I think we're at an exciting moment, as I mentioned, not just for edge AI, but also for smart glasses and AR. This year, at this show and over the next 12 months, I expect most of the large consumer players to launch products. And I think what this is going to do is really give consumers an opportunity to test and give validation and feedback to these companies about how to improve. And I think over the next 2 to 3 years, we're going to see what kind of technology, features, and functions are going to be adopted and really optimized for. As I touched on, in about the next 2 to 3 years, I expect display technology to continue to mature, both in the terms of the performance it delivers, but also the power consumption side, as well as launching that next generation of sensors, driving that edge compute along with the SoC. And last but not least, the spatial compute will become seamless, and I think the user interface will also become seamless. And I think as these two mature, also the way we interact with the glasses and the way it takes the real world around us in, and leveraging AI, will really become a fantastic experience for users. So combining that experience with all-day wearability by weight and power, I expect the flywheel will take off. So to drive it all home, again, physical AI is taking off to automate and augment the human experience. We believe smart glasses are the key form factor to connect us to the real world and also to the power of AI. And we think adoption currently is being limited by size and power, of which sensors will help through pre-inference and then driving the power consumption of the devices down. And as AI's exponential growth continues, we expect more compute to come to the edge. And through that edge compute and context awareness, we can unlock the flywheel by driving power down and privacy up. This is the vision and future we have at TDK, but if you'd like to see some of these new products that we're launching and see them in real use cases, feel free to stop by the booth. We're at booth 1234. That's not a typo. Count them out with me, 1234. Stop by, we'll be happy to show you a demo and you get to experience these amazing sensor technologies in the real application. Thank you very much.
Let's give them a round of applause, folks. Now, we do have a couple minutes left for a quick Q&A if anybody has any questions.
Hi, great presentation.
Thank you.
I was wondering about the gaze detection. It's basically eye tracking, right?
That's correct.
Is it ultrasonic or optical based?
Right now it's optical.
Optical.
The video you saw is an optical-based solution. Yeah.
Okay, great.
Correct. We are looking, though, as seeing how potentially ultrasonic could eventually replace that. That could be a potential way forward.
Anybody else have any questions? Anybody want to
Yes.
So as I know that you have the 6-axis IMU sensor, but
Yes.
I was just wondering if a magnetic sensor can be also embedded and integrated into this IMU sensor as well.
Yeah, fantastic question. So basically, what we do is we take the 6-axis IMU, so it's 3 axes of acceleration for linear motion, 3 axes of rotation, and we combine that with our TMR sensor that I mentioned, and so you get true, position relative to Earth's magnetic field. So that's where the true heading is enabled. We actually combine that with software to do sensor fusion. So that's that feature I was mentioning where you can really get true north navigation with the 9-axis solution. And we offer the full suite. It's called PositionSense. And that's one of the products we've been launching recently and seeing a really wide adoption.
Yes.
And actually, this is true for all of the solutions. So VR, smart glasses, smartphones, you can see it everywhere. And again, it's the lowest power approach as well.
Got it. Thank you.
Great question.
Time for one more question. Anybody has any burning questions or desires to ask? Right on. Have a question?
Hi. Thank you. Great presentation.
Thank you.
I had a question about the location of these sensors and how you think about the location and the power. So I was wondering if there are certain positions in which we could put these sensors, like maybe, for example, closer to the SoC or something that helps you save power. Have you kind of thought through that angle?
Yeah, that's another great question. So as I mentioned in the talk a little earlier, of course we're trying to reduce the routing because that's a significant challenge, just to build it, but let alone to add weight. But oftentimes the sensor location is determined by the feature or function it's trying to enable. So for example, in the case of microphones, we're going to want them kind of on the arms. But in the case of the IMU, sometimes we'll place it on the bridge closer to the SoC. So usually I would say from a compute perspective with respect to the sensors, the most compute-intensive sensor is probably the IMU. And so as a consequence, it usually finds itself closer to the SoC. But one of the things we need to keep in mind, and there was a great talk earlier this morning about this, for the glasses, we can't have the glasses rise above about 38 degrees C. So again, the way we distribute the compute across all these different chips is also important. It'll allow us to not have to throttle back or, in the worst case, shut down the compute and really give that more seamless, low latency experience to the consumer. Yeah.
Thank you, Omar. Everybody, please give Omar one more hand, please.
Thank you very much.